Good morning. It's a real pleasure to be here. I'd like to thank Professor Musallam and other staff at PIER for the invitation and an opportunity to share with you some of the things that I've been working on and some of the thoughts that it's in connection with the topic of the session. I will be focusing on bridges. Let me just start by reminding us about the fault line just in the Bay Area and the bridges that we have in this area. Now, let's say that these bridges all meet the current seismic code, seismic standards. They are designed to withstand earthquake without collapsing. They're not designed to be functional after the earthquake. And if you take a subset of these bridges, let's say 20% of them after a strong earthquake, you can imagine the kind of impact that's going to have on the whole area, and it's going to be far-reaching, and it could even have effect for the whole country, could affect the international commerce and all sorts of things. Again, the issue is that our bridges are designed not to collapse under strong earthquake. That has been our primary criterion in our bridge design. So the way we judge our failure and success is whether we are preventing collapse or not preventing collapse. So based on that criterion, this is obviously failure. This is the superstructure of a bridge. This is the column. It used to be a column. But this one is success. We are ready to open a bottle of champagne, start smoking cigars, and say, hey, we did it. This is the right engineering. Obviously, the public would not buy that. And also, what happens to the community and the region after the earthquake becomes very, very questionable and not defensible. So our thinking is that, okay, preventing collapse is fine, we should do that, but in addition to that, we should also think about what happens after the earthquake. In other words, no collapse design is not sufficient. So serviceability after the earthquake has to come into the picture. So when it comes to bridges, really there are two things that we have to take care of. One is the damage in plastic hinges of columns, and the other one is controlling the permanent drift. These are the two main things that make bridges dysfunctional after the earthquake, even though they have survived the earthquake. Now, we could think about performance-based design and broaden the meaning of it. It's not just performance during the earthquake, also performance of the system after the earthquake. We could do that. There are other tools that have been around for a while. The base isolation is a tool that can prevent damage. But there are also other areas. Those are advanced materials, and I'm going to talk about some of these. They involve using things that we are not used to. Shape memory alloys, ductile concrete, post-tensioning of our bridge columns. It's pretty unusual. And other means. And of course, the ultimate goal with that is to go back to the very simplified plot that I suspect you're going to see that a few times during this conference, that this is where we are now. And our ideal situation is that the bridges do not know that there was an earthquake. That would be the ideal situation. So let's talk a little bit about these issues. And I'm talking about new construction. I'm not talking about substandard bridges. Okay, this is new bridges. These are bridges that meet current code. That's what I'm talking about. So we have plastic hinge damage. Yes, again, both of these bridges are considered to be successful design because they did not collapse. But we have obviously major damage where these bridges cannot be used. It can also be permanent drift. This is about 100 bridges after the Kobe earthquake were torn down because of permanent drift, it wasn't because of major damage to plastic hinges. And the bridges did not feel safe. So let's get to the cause of this. Why is it that we have plastic hinge damage? So if you look at the stress strain diagram of concrete, in this case I'm showing an unconfined concrete. As we start cycling our load on a bridge member, in this case in a bridge column, we begin to have some spalling. That spalling begins to extend into the core, and eventually we have the type of damage that typically you expect from reinforced concrete structures. Even though the column may be stable, but still it undergoes this kind of damage. So that's what was causing the problem. We're using concrete, the unconfined concrete, as well as confined concrete eventually gets damaged as well. Now, if you look at permanent drift, the primary culprit is the steel reinforcement that we use. The stress strain diagram for steel, we are designing our columns so that they yield under strong earthquakes, but that yielding means that there is permanent strain. In addition to that, there's damage in concrete, and that leads to permanent deformation that we experience. So we need to address these two issues, the permanent drift and the plastic hinge damage, in order to make things work. Now, to reduce plastic hinge damage, there are a number of ways, there are a number of things that researchers have been looking at. Things such as the engineered cementitious composite. It's basically a grout that has fibers, so it's a fancy name, but it is what it is. The ultra-high performance concrete that, again, has been studied. Built-in elastomeric rubber pads. These are not base isolation systems. These are the kind of material that are used in base isolation, but they're part of a column, and they're intended to work in flexure. Or you could have also fiber reinforced polymer. They can also reduce the plastic hinge damage, or eliminate under even strong earthquake. To reduce permanent drift, post-tensioning of columns with steel tendons or CFRP if you want to make it more durable. There are other alternatives. There are super elastic shape memory alloys that could be made from nickel and titanium. Yeah, there are things that we are not used to. We structural engineers or bridge engineers are not used to this kind of thing. Or using copper or aluminum, there's a new generation of that's coming, iron-based shape memory alloys. And also fiber reinforced polymer, they tend to reduce permanent deformation. So post-tensioning alone would provide this recentering. These are CFRP tendons that can be used for post-tensioning. For super elastic shape memory alloy, the basic stress strain diagram is a flag-shaped response, meaning that when the strain goes back to zero, when the stress goes back to zero, the strain also goes back to zero, unlike steel, where you would have the path that the stress strain diagram curve would follow, would come all the way here, and that give us the permanent drift. So these have been some of the ideas that have been explored, have been studied, and to just give you some examples here, this is where we have a column where we use a CFRP tendon. It's tested on a shake table, and the cluster around the origin that tells you that column kept coming back. At the end, when there was a rupture fracture of longitudinal bars, then we had, of course, a different story. But this allows us to eliminate or substantially reduce permanent drift. The shape memory alloy combination with the ECC is an example of that. You notice that flag-shaped response that I mentioned is maintained in a column. This is the column that was tested, and you notice that the shape is flag-shaped. Also here, the fact that they come back to the origin, that tells us that we don't have that much residual displacement, pretty much negligible. And when we use FRP2, we do not completely eliminate, but there's a substantial reduction in permanent drift as well. So when we combine some of these materials, what are we going to get? Here's an example of two columns, identical columns. One use conventional reinforced concrete, and the other one use shape memory alloys and ECC under the same drift level. This is the kind of condition, this is the kind of damage that you see here. In the bridge with this column would have to be shut down to traffic, whereas here we do not need to do that. Post-tensioning alone, we have tried that with conventional concrete. We see that there's still, even though we eliminate or substantially reduce permanent drift, there is some damage in the plastic hinge, so we are not completely eliminating that. When we substitute the regular concrete with UHPC, this is the kind of thing that we get under the strongest, the maximum credible earthquake that this column was designed. And in terms of quantifying that, if I share with you the residual drift ratio versus the maximum drift that we have applied for conventional column, this is the kind of permanent drift that we had, whereas by going to SMA, we are reducing that by about 85%. So there's definitely evidence that yeah, these things could work and could make our structure functional. So okay, well, that's wonderful, laboratory environment, and what is that going to do for our engineers? What can they do? So are we dreaming just that this thing might happen sometime, or do we have any codes? Do we have any guidelines? Do we have any tools to give our designer? And the answer is yes. There was a project that we completed just a little over 2 years ago. It is funded by the National Cooperative Highway Research Program. We did this project in collaboration with Majesty and Masters. It's an outfit that writes most of AASHTO structural design codes. So we work with them to make sure that we have something practical, something palatable. We also work with the Berger ABAM of Seattle to come up with design examples. So it's not just a dream. There are some preliminary tools that have become available with design examples that would open the door for using these advanced materials. I'm pleased to let you know that we implemented one of these innovative concepts using shape memory alloy and ECC in a bridge in Seattle, Washington, with funding from the Federal Highway Administration and the Washington Department of Transportation. This was a 3-span bridge and supported on single columns. And this is the superstructure. So our focus was, of course, on the columns and used the shape memory alloys and ECC combination in that bridge. There was some additional research that we had to do to optimize the way we connect these shape memory alloy bars and the length of the bars. And these are some of the columns that we tested. We started with our reference column. And these are 2 other columns that use shape memory alloys and ECC with different lengths, because that was one of the objectives of the study, to optimize the length of these. And of course, they did work. And this was implemented in the bridge. So here you see a close-up of these are shape memory alloy bars, like number 10, equivalent to number 10 shape memory alloy nickel titanium bars that are connected to steel bars above and below, because we don't need to use them over the entire length. The bridge was constructed and was completed and became open to traffic last February 2019. Now, and this project has received a lot of recognition. And the point I'm trying to make here is an important one. And that is, of the 4 awards that you see over here, 3 of them were selected by practicing engineers. Okay? It wasn't by other researchers who were impressed by the research and the implementation. What that tells me, that the practicing engineers, at least there's a group of them, they're very progressive, they're ready to embrace new ideas. Okay? We don't necessarily have to stick with what we have been doing in the past. We have to at least explore new ideas. And there are engineers out there who are very willing to look at these things. The NCHRP project that I mentioned, it was funded by AASHTO essentially through NCHRP, and the project was selected. The topic was selected by practicing engineers. So it's very encouraging to us researchers. Now, we have been asked to talk about future. We human beings, we're very good at predicting what we want to do in the future, but we're pretty bad when it comes to how we get there. So there was a time that we dreamed of flying, right? So that was the what part, but the how part was this, okay? Didn't do very well on that one, but eventually we got there, didn't we? Okay, just different ways. There was a time that we predicted that, oh, these binoculars that we're building are going to be so powerful that we can stand in Los Angeles and look at New York. Well, interesting concept. The what was fine. The how part was a huge binocular. In reality, we have done that. We have FaceTime. Allows us to do that. So my point is that, yeah, we can talk about all the paths to the future. We know what it is that we want to do, but when we get there, maybe it's going to take a few iterations. So the ultimate goal, of course, is this. The what part is very clear. We want to have functional structures. So now we can even take this further. Now this one you can say is a dream. Can we look at the emergent technologies and use them? Well, there are certainly indications that yes, we could do that. We have done some trial applications here and there to show that yes, it is feasible, it is possible, but we should be willing to adopt other technologies to use that. But again, parallel to this, if you go back 50 years ago, when we began to use fiber reinforced polymers in structural engineering, no one predicted that we could have such a widespread use nowadays. It was something that came mostly from the aerospace industry, extremely expensive, very specialized, but we adapted. We found ways of using it, bring the cost down. It is okay for us to have concept bridges, just the way the automotive industry has concept cars. They were thinking of that someday we may have cars like this, but now I have one in my garage, so this can work. And again, looking at the future, why not try to make our bridges deconstructible? About 10% of the bridges about half of the bridges that are demolished in the U.S. every year is not because they have a structural deficiency. They're demolished because they have functional deficiency. There's nothing wrong with the bridge itself. Why don't we start making bridges that can be undone and taken somewhere else and can be reused? You know, you talk about environmental impact and not using more concrete and cement and all of that. Why not do that? And meanwhile, while you're doing that, while you're making the deconstructible bridges, why not bring in these new materials and make them so that things can be detached and reused somewhere else, or if there is minor repair needed, can be done. So what it is that we have learned from recent research is that it is feasible to get into novel materials to use them. And there are barriers, no question about it. I had to deal with that. But they're not insurmountable. We can deal with them. We can handle them. We like challenge, don't we? So, and we do need to convince engineers that life cycle cost has to be considered, because the initial cost of a bridge may go up by 3-4%. Okay, but you have a bridge that will remain functional after a strong earthquake. So there's a trade-off. And this other one, we're talking about design guidelines, and they really need to evolve a lot faster than reinforced concrete. We have been studying reinforced concrete columns, connections, for the past 70 years. Okay, and we are still doing it. We are still testing bridge columns because there are additional information that we are still seeking. We're trying to fine-tune our work and learn more. Okay. Well, maybe when it comes to novel material, we don't have to wait 70 years to do that. Maybe we can start using them and learn as we go, just same way that we did with reinforced concrete. It's perfectly all right to be evolutionary in this business. And so how are we going to get there? My thoughts are that we should start talking to materials engineers. Structural engineers need to talk to materials engineers and be patient with them and ask them to be patient with us, because the way we communicate is very different, okay? But we need to do that. We need to take the time and do that. We need a lot more research and to generate information. And I'm not saying put everything on hold until research is done. I'm saying that we need more stronger database. Look at the database that we have for steel and concrete versus the database that we're dealing with in shape memory alloy. There's no comparison. So we need more of that. That means we need to learn a lot more about materials and components and structural components, structural system. And our modeling, right now we have been basically doing patchwork, okay? We are taking what's out there for reinforced concrete, and we are taking those and trying to squeeze them into something that's applicable into shape memory alloys and UCC. Well, maybe we should take another look at that and come up with things that really are directly applicable to the novel materials. So with that, I'd like to leave you with these thoughts and hope something will trigger your interest in looking at other kind of material and other approaches. Thank you very much.